That's fine. So welcome. My name is Stuart Middleton, as said. I want to give you a little, I've been invited to give a little sort of keynote or sort of introductory talk about large language models and my research around information extraction and information retrieval. There we go. I'm going to cover different aspects. I'll first of all introduce large language models for anyone who isn't familiar with those, or I suspect many people are starting to get used to those. Then cover a little bit about my research around information extraction. So in particular, multitask learning, graph convolutional networks, and in-context learning, which is a few-shot approach. And then finally move on to information retrieval augmented QA, which is question answering systems. Okay, and I'll conclude with a couple of slides on a couple of my projects. Right, so for anyone that doesn't know me, so my research is around natural language processing. So in particular, I've been looking at things like large language models. That's my sort of day-to-day research and different aspects around those. I have a number of grants there, but in particular, I'm focusing on information extraction and also human-in-the-loop approaches for natural language processing, which includes large language models. Okay, so a little bit of an introduction to the models. So large language models, they're obviously in the news at the moment. They've really made a step change in terms of both fields, certainly natural language processing, but that's bled out into fields like information retrieval as well, because the performance you get from them is pretty undeniable now. There are two types of large language models which are predominant. The first is a masked large language, typified by the BERT models and the various variants of those. Typically, these models are trained with under 1 billion parameters, and a masked large language model, it's been trained with a task, so it's given a bit of free text, a bit of human text. Some of the words or the tokens are masked out, and the model has to predict what those tokens would be. Okay, that's the basic task. It's pre-trained, and then it's usually those models are fine-tuned for your particular downstream task, which could be a number of things. It could be a classification task, question answering task. There's a whole load of different options for those, and they're particularly good at things like classification tasks. Whereas the other type of model, which is typified by the GPT series, is generative language models. So this, back in 2017, we had GPT-1. At that stage, BERT and GPT were both available. Typically, we would just natural language processing researchers, we would use the BERT model because it was better. But as you can see, OpenAI has slowly increased the size of their model, and that increase in the number of parameters you can see here goes from GPT-2, which is 1.5 billion parameters. Then we have 175 billion for GPT-3. That's when it started hitting the news. That's the point where it's starting to generate human quality text. Okay, the latest is around rumored to be around 1.8 trillion. They don't actually reveal the exact number. Okay, that's ChatGPT. That's the thing that you can use for the day-to-day. That's the commercial offering they're provided. However, there are other vendors. So Meta produced their Llama model. That's now Llama 2. They produce that in a range of models. Also, Google have released the Bard model. Okay. So these are typically the commercial models, but there is a lot of open source available. So interestingly, Meta chose to release open source their Llama model. Okay, and that's allowed the academic community to really take that on and start to play around. So we're getting now a lot of variant models, things like Mixtral, Tudelu, Flan, Palm. They're pretty much every month there's a new model coming out. It's really quite an exciting time to be in this area. And these models have a range of different parameters. And what this has done is it's allowed the academic community to bring some of their expertise and particularly a couple of kind of older techniques that they've reintroduced to the large language models that players like OpenAI had missed originally. So I've highlighted a couple of these. The first is low rank adaptation, LoRA. That's an algorithm which would allow the model to be trained a lot faster when it's fine-tuning. So typically what you'd do is you'd freeze this very large model, which might need a cluster that's been trained with, say, 1,000 GPUs on OpenAI's cluster. You would take that model, freeze it. You would then create a set of similar weights, which are a lot smaller, so the rank's been reduced. And those are the ones that you train. You can train that very fast. You can train it on a single GPU or a couple, 2 or 3 GPUs. It's a lot more practical. And that's what a lot of people are doing now. And also quantization. So this is where the large model, you take it, and for your downstream task, you actually identify which areas, which patterns are most appropriate, most useful, have information value for your task. And you reduce, for all the other patterns, you reduce the actual bit size of the weight matrix. And this has the effect of shrinking the models, which is, but without at the expense of a lot of the performance. So, for example, I think the Palm model, 540 billion, that was able to be shrunk to a parameter size of something like 7 billion, which you can run on a single GPU with a loss of around 10 to 20% on the performance on some of the key benchmarks. So you can see academics are finding interesting and novel ways now to take these very large models, very expensive to train, but actually shrink them, make them a lot more practical, and then do really interesting things with them. Okay, in terms of information extraction and information retrieval, as I say, we're now getting pretty near human quality results in terms of generation. Partly this is due to companies like OpenAI running reinforcement learning sessions with real people talking to the models and improving their kind of human dialogue skills. But also it's really it's down to the size of the models which allowed that. And what we're seeing is some real step changes in things like dialogue, that's the chatbot, that's ChatGPT, but also tasks like question answering, summarization, text classification, things, and also simple reasoning tasks. It can now do maths. It can do an elementary maths test pretty well, some of these models, okay? It cannot do complicated reasoning yet. These models do not truly understand anything, but they are extremely good at finding co-occurrence patterns at increasing levels of depth within the neural network, which is allowing them to do simple reasoning tasks. Okay, challenges. So as you've probably seen in the news, generative models do suffer from things like hallucinations. If you ask them to generate a new research paper, it will produce a very convincing research paper, but it will probably make up all the citations. They won't exist. And it will get some things right, parroting from wherever it's trained, but a lot of it will be just fictional rubbish. Okay, also suffer from information loss. So if you ask them to summarize text, it will probably get quite a lot of the key points, but you won't know the points it's missed. And it will be extremely assertive and authoritative. It will say, this is the summary, no room for doubt, but actually it's missed out 2 or 3 of the key points. A particular problem for students trying to generate their coursework with these generative AIs, which we mostly do not allow at the university. Okay, so that's generative models, and then master models, they don't suffer from the same sort of hallucination and information loss properties, but they are incoherent if you ask them to generate text. That's where the master and the generative training comes into play. But both of the models suffer quite badly from the bias in the original training data. It's trained on web crawls. I think the update, you can't quite have it as crude as up to 2021, but that's what it was originally trained. Then now the companies are updating them, but they have a historical bias. They are trained, all of the data they've trained in, which is basically crawls from the web, that has things like gender bias and racial bias. That's all built into there. That gets transcribed straight into the model. So unless you have safeguards, which guardrails, which the companies are trying to put in, you will get models which exhibit those types of bias. And also there's a lack of uncertainty. So the outputs to the model, they will be there's no kind of error with them. They just, here's the answer. Okay, it's up to you to decide if that answer is missing some data, it's just wrong, it is correct, who knows. And that's quite a big issue for application areas like critical areas like mental health, healthcare, defense, things where decisions made on the output are actually going to be really important. Okay, I put that question right at the bottom for this audience, a provocative question perhaps. There is a lot of work around large language models to essentially build the new generation of search engines. And there is a question I'll put out there, which I won't answer, but if these models get big enough, do we need search at all? Can we just use a large language model? There is certainly the trend is that way, but who knows where it's going to end. Okay, so now a little bit about my research. So I'm going to give you some master language model examples, and then some generative model examples, some of the latest. So this is work back in a couple of years ago. It's the CL-Psych is one of the major natural language processing mental health challenges. We won it this year, won it this year as well, actually. So the task here is to use a BERT-based model to encode text around mental health conversations. And what we're trying to do is to identify the moments of change of mood of people over time on a Reddit forum, in this case, I think it is, and then also the suicide risk classification as well. So it's kind of a 2 tasks that we've trained. The actual data set, it's around 6,000 posts and about 180 users. So, a smallish data set in NLP terms, but it's annotated by humans in terms of the data. And what we do is we use a combination of large language models. So RoBERTa is a model trained for emotion type text classification or embedding. Sentence BERT is a classic sort of BERT-based approach that can handle slightly larger content. And then fast text is one of the older models. We concatenate all three of those. We embed the text using those models, concatenate them together. That provides the post embedding, which is the bottom layer. We then feed that through to our domain-specific layers, which is the bi-LSTM, the bidirectional LSTM model, and an attention layer on top. So F1 scores of around 0.6 for the moments of change, the change in mood task, and around 0.45 for the suicide classification. So, okay, but not fantastic. If you want it perfect, it's 1. Okay, so you wouldn't be basing any medical decisions on that, but maybe it could give you some guidance to triage a large intake, and typically work with people like mental health forum providers who have a big intro each day. So it's quite helpful to rank that. But you'll see it gets a bit better as we go. So then we added in a graph convolutional network. So we thought, right, what that system, and then build in a little bit more graph-based approach and introduce information from both the kind of graph nature of the conversations. People post, people reply, there's interactions. We want to try and encode that. So we did that we also tried to do a little bit more principled approach to classify the moments of change. So in this case, we used a bigger data set. You can see it's now grown to 28,000 posts. Still read it, but we used a psychologically motivated model to do the classification. So here we're looking at valence and arousal. And if you have changes of those, we can then infer changes in mood. A little bit higher quality approach than just relying on a simple sort of emotion classification or a sentiment-based approach. Again, we used a similar approach. What we're doing is simply in terms of the architecture, we're just adding in a graph layer, okay, to on top of that. So we're replacing the bi-LSTM and sort of inserting a graph layer on top of that. But this time you can see at the bottom right, you can see we're adding in different layers. So we have a graph network representing the conversation in terms of its post-reply graph. Okay, so who's talking to who? There's a graph representing the emotional state. So these posts are angry, these posts are sad, that type of thing. And a graph representing the sentiment, so positive, negative, for or against type thing. And each of those are then fed into the layers of the convolutional neural network, and that then provides an additional feature space which delivers some performance advantages. So a little bit richer in terms of the representation. So you can see here our F1 score, it's gone up slightly. This is actually, remember, this is a slightly different data set. It's a harder data set. So although the score is quite similar, it's actually a lot better because the original model is, you can see at the top, has gone down a bit because it's a harder data set to work on. We have more mental health topics we're classifying. In terms of that, we're now up to 0.85 in terms of the F1 score. So this is into the level where you might actually want to start using that. Okay, that's not too bad on the error rate in terms of the mental health classification. And we've been talking to some mental health providers in terms of using this type of thing for triage in terms of large in-trays. Okay, now we move to the latest stuff. So this is this year. So we've won the task again, which is happy days. This work is about to be published. The conference runs in March, I think. So this time the task is slightly different. It's still mental health, but it's looking at suicide evidence extraction. So not just labeling a post as has a suicide risk, but actually which bits of that post are important to that decision. And then also summarizing it in a human way so that a moderator, for example, can see a nice paragraph of text explaining why the model thinks that there's a suicide risk there. So you can see a little bit more challenging task. We're trying, the whole workshop was trying to use the power of the large language models to explain and reason about why they're making these decisions. Okay, this time we're using the suicidality data set. So this has been annotated by a set of crowd workers, but also clinicians. So a small number of more clinically labeled data sets. Okay, and then you can see the models below that we're using. So the large language models we're using, some of the latest, the kind of the 7 billion and the 70 billion models. We wanted to compare the two, how the size of the model impacts the performance. And we're using what's called in-context learning. So for these large language models, what we're doing is we're not fine-tuning them. They're quite big. We didn't want to do that. Also, the task was quite short, so we didn't have time. So instead, what we're doing is we're providing in the prompt to the large language model examples of what we're after. Then we're asking the model to have a go at that post where we don't give it the answer, following basically with the context of those examples. That's why it's called in-context learning. We also do what's called chain of thought prompting, which is a technique where we do exactly the same, but we break it down step by step. literally using the words "let's think step by step" as the prompt. This is has been shown by researchers to resonate with some of the pre-training. My own hypothesis for this is it resonates with the reinforcement learning. So some of the sessions, people have been, let's think step by step, and that way it happens to work quite well. But what we're doing is we're thinking step by step in terms of the aspects of the mental health criteria, which the decision will be based on. Okay, I've got some examples for that. So it might be a bit small. I'll try and talk you through it. So at the start, the top bit of text, I blanked out the actual post because it's obviously somebody's post around suicide, so we're not putting those in the slide. At the top is essentially some guidelines. Now, this is literally just text for the language model, but what it does is it allows the language model to connect some of the neural pathways that's pre-learned, and that's been shown to generate a much better result at the end. If you just have a prompt, say, give me the answer, or what's the mental health top of this, okay, it won't do as well as if you give it a nice breakdown like this, some guidelines, okay? These guidelines are around the aspects that we want the model to consider, and these are things like emotions, cognition, behavior, risk levels, okay, and some explanation of what they are, okay, in terms of human terms. And what that does is that helps the model to kind of associate patterns, co-occurrences, which then allows it to get an answer which is more relevant to those types of attributes. Then we, in the bit that's blacked out, we then provide an input example. So that's the post of the Reddit post that we want to classify. This is the in-context example. So we'll also give it the answer. So we say, right, here's the summary without the meta information. Here's the summary with the information. This was what the task needed. We then proceed to give it some input which you haven't classified and say the model, right, essentially what's the answer? We come up with a nice prompt to allow it to generate. It will then generate its own version of that, and it does it pretty well. In terms of the chain of thought prompting, so this is where we break it down step by step. Okay, this is the type of thing we do. We basically say, you can see it says at the top, output, let's think step by step. Emotions, bop, bop, bop. Here's some extractive text from the input that relates to emotions. Then we have cognitions. Okay, so this is the example where we give it the sorts of things that it'd like to do. We then ask the model to generate its own thing. So we literally say, let's think step by step, and the model then generates the rest. It will learn to generate the emotion extracts, the cognition, then it will generate the answer below. And it's been shown, research has shown that in doing that step-by-step generation, the actual final answer is better. So even if it gets those cognition steps wrong or it picks out the wrong thing, it doesn't actually matter. The end result will actually be better. So this kind of guided generation just generates better results. Stopped it again. There we go. Okay, so you can see now we're up to 0.92 in terms of the F1 score. These language models do deliver meaningful performance. That's a lot better than we could achieve with the BERT model. If we were to allow the BERT model, so one of the benchmarks, you can see the 0.924, the supervised approach. That's an example where we've given it a training data with lots of supervised examples, whereas the few-shot approach using the large language model had 2. Okay, so it's just a few shots, hardly any training. If we do 0 shot, no training at all, it's still doing pretty well. So it's obviously learned quite a lot about the concepts that we're trying to ask it to do already in its pre-training. That's the value of these massive parameter space models and the very large corpuses they're trained upon. Okay. And then, so the top is the evidence extraction, the bottom is the summarization task, which is obviously 0 shot. We didn't have any example summaries. So again, that's pretty high, it's 0.97, okay? So these results are getting really quite good. This is to the level where it's actually quite useful, I think, for potential downstream applications. Okay, now obviously we want to cover a little bit about search as well. So this is I have a new grant starting, which I'm not allowed to reveal yet because it's going to be announced soon, but it's in the engineering domain. So what we're going to look at is information retrieval augmented question answering approaches using large language models. So we're going to base this is new work, it's kind of just started. We have started the project, it just hasn't been announced. We're looking at 2 approaches. The first is retrieval-based generation. The second is large language-based generation, and then question answering. So we're basing it on what's called the dense passage retriever model, which some of you may be familiar with, but I'll recap it. So here, the initial query, which you want to pose, that's then fed to an information retrieval approach. In this case, it's the paper we're basing it on is TF-IDF, or BM25 is actually the better ranking algorithm that works. And then the large language model was a masked large language, so it's BERT, although we'll be playing around with some of the latest generation of generative models. Okay, we'll bring this work is based 4 years ago, so that's like ancient in large language model terms. So the idea is that the model with the retrieval part is trained to rank documents. So it gives a load of we give it as training text passages, and we provide the passage index from the document it comes from, and then it learns to essentially associate text with the documents that are in its index. That is then used once we've done training, then we provide it the same query, but this time it will actually learn to essentially return the k most nearest passage indexes. So it's learned to kind of rank the documents most likely to have the answer, and then it can also be trained to actually generate the answer itself. In terms of the generate and read, what we do is essentially, this is based on work from last year, and quite a few of the more modern approaches are following this approach. Rather than do the search part, rather than do a BM25 algorithm to search and rank, we just use the large language model and train it on the data straight away. So here we essentially, the query, again, it's 2 steps. The first, the generate step, we actually use the large language model to create the documents from scratch. Okay, rather than retrieve documents that exist, we create and generate the documents. We specify, we set the temperature for the large language model so that it's maximum diversity. So we create 100, 1,000 different versions of the document. They are then ranked in terms of their relevance to the answer. Okay. The second step is then, given a set of generated documents, what's the answer? Okay, so the documents are purely generated, and it's using the power of things like ChatGPT to basically that massive pre-learning to generate that input in the first place. So in this case, the authors used Instruct GPT. So it's a 175 billion parameter model. That's similar to GPT-3. I think it was based on that. And you can see it uses in-context learning again. So the ideas that we had in the mental health domain, we can transfer to here as well. Okay. So just to shout out to a couple of the projects as I finish. So the first is around the Protect Them grant, which is running. So this is a interdisciplinary project. It's running with social scientists as well as computer scientists, myself. And this one is looking at share renting behavior. So share renting is where parents post information about their children that in later life can be endanger them. Essentially, like images of them being naked in the bath or identity information, which can then expose them to cybercrime risks. Things like child pornography, identity theft, putting. And what we're doing is using large language models to identify behavior markers. It's too challenging to identify share renting. It's too subjective. So what we're going to do is identify behaviors that we know we can train the model to do, which can then, as an aggregate, help the, in our case, criminologists, assess a set of forum posts or for downstream user moderators in order to identify the risk level based on the behaviors which the model is automatically classifying. And we're going to use, we're using a human in the loop method in order to iteratively use the models and train the models. So what we're doing is we're having sessions each day. There's a session where the language model classifies the content online. The criminologist assess it for risk, updates the examples. The model is retrained overnight. It's run again. And that happens for like 5 days in a week. We're running kind of week-long experiments. So it's an example of how these models can be incrementally trained. The idea being that given a few sessions, the model will learn to be a good share renting classifier. And this could be applied to a number of different kind of online classification tasks. And then lastly is the project I can't announce yet, but it is a major initiative looking at large language models being trained for both question answering and code generation in the engineering context. So we have a large engineering company. It's an Innovate UK grant, and in the next month or two, we'll be releasing it, and the university will probably put out some announcement or something. So thank you very much. Very happy to have any questions.